In this video, I want to talk about balancing the combustion equation, and then at the end I'll give some examples and also talk about air-fuel ratios. A single hydrocarbon fuel will have the general formula CHO as shown here. It might also have nitrogen or sulfur components or even other atoms besides that. However, I'm currently only going to consider a single species fuel, in other words, one homogeneous fuel. The general combustion reaction converts the hydrocarbon into CO2 and water. For its oxygen source, it uses air in a stoichiometric amount so that the number and type of atoms on the product side will be equal to the number and type of atoms on the reactant side. Also, nitrogen from the air is carried through the reaction and in some cases may even participate to form oxides, so we will carry it in the equations just as part of the air. Air is composed of 20.9 parts oxygen and 79.1 parts nitrogen. It can be written as 1 molecule of oxygen plus 79.1 over 20.9 parts nitrogen, which, as you can see here, if you just do the arithmetic, that's going to be 1 oxygen molecule, 1O2, and 3.78 N2 molecule. To obtain the average molecular weight, you take the fraction of oxygen times the molecular weight of oxygen plus the fraction of nitrogen times the molecular weight of nitrogen. You can see here that's going to give 28.8 grams per mole or kilograms per kilomole as the average molecular weight. When you're using the average molecular weight, it is important to note that you're actually going to have 4.78 total moles of air. There's 1 mole of oxygen, 3.78 moles of nitrogen, so that's going to be 4.78 moles. In the general combustion equation, the alpha, beta, and gamma, written also up here, refer to the number of atoms, respectively, of each type of atom. So, for example, we will have alpha carbon atoms, beta hydrogen atoms, and gamma oxygen atoms. Any of these could be 0. No, I'm sorry, only the oxygen could be 0. Otherwise, it wouldn't be a hydrocarbon. You must have at least the carbon and the hydrogen. In this equation, we're showing the fuel plus the air, in the parentheses is the air. On the right-hand side, we have the CO2 and the water, and then the excess nitrogen. And the amount of nitrogen appearing over here obviously has to be the same as the amount of nitrogen coming from the air. The subscripts, alpha, beta, and gamma, will be given by the choice of fuel, but we need to find values for x, y, and z. X is this coefficient, y is the coefficient of CO2, Z is the coefficient of water, W is the coefficient of nitrogen. We need to find these in order to balance the equation. Notice that I've used exactly 1 mole of the fuel, so there's no coefficient in front of the fuel. I will show an algebraic method for finding the coefficients, X, Y, and Z, and W. There's a more traditional method, but it's actually less reliable. It depends a great deal on intuition. It can be faster if you know how to do it. Let's begin by writing 4 equations with the 4 unknowns, x, y, z, and w. Alpha is the number of atoms of carbon appearing on the left. On the right, carbon only appears in one place with the coefficient y, so alpha must be equal to y, and that's how you equate the carbon atom. There is also only one source of hydrogen atoms coming from the fuel, so there are going to be beta hydrogen atoms. If you come over on the right, the hydrogen appears as H2 and only as part of water, so it's going to be 2 times the coefficient of Z. Therefore, beta will equal to 2Z. Oxygen is going to be the most complicated of all. We have gamma oxygen atoms as part of the fuel, and then we're going to have 2 oxygen atoms in the air. Our coefficient on the air is X, so we'll have 2X oxygen atoms still on the left side. On the right side, we will have 2 atoms as part of the CO2, and they're multiplied times Y, so we'll have 2Y. And then finally, there's going to be 1 oxygen atom in the water, and that's going to be a z for the coefficient, so that's only going to be a single z. The nitrogen can be just a little bit tricky. We have to pay attention at least. So we're going to have two nitrogen atoms in the nitrogen molecule, but then there's 3.78 moles of that within the air, so that we're going to have 2 by 3.78 by x, 2 by 3.78 by x on the left-hand side. And on the right-hand side, we have pure nitrogen again, so that's going to be 2 atoms times our coefficient W to give the final equation. Now we need to solve these equations from for x, y, z, and w. We can look at this by inspection. We can see that if alpha is equal to y, then y must be equal to alpha. Similarly, if beta is equal to 2z, then z must be equal to beta over 2. In the third equation, we can transfer this gamma over to the other side. We've done that right here, so then we have 2x is 2 alpha plus beta over 2 minus gamma, and then we'll fill in values that we've already found for the y and z terms, so we'll have x is equal to alpha plus beta over 4 minus gamma over 2. The final equation is equally easy to solve. We can see that w is equal to this left-hand side. If we simply divide through by 2, the 2 goes away, so w is going to be 3.78x. But we've already found out that x is equal to alpha plus beta over 4 minus gamma over 2, so we take that piece and put it in place of x, and w is 3.78 times this expression right here. Finally, we can write the balanced equation only in terms of alpha, beta, and gamma. So alpha is the number of carbon atoms, beta is the number of hydrogen atoms, gamma is the number of oxygen atoms, and now the coefficient for air is in terms of alpha, beta, and gamma. There's the air right there. Over here we have alpha, CO2 molecules, we have beta over 2 water molecules, and we have this many nitrogen molecules. So that concludes the algebraic method for balancing the stoichiometric hydrocarbon fuel air equation. So we've developed this balanced equation. Now let's run through a couple of examples in using it. In the first example, we'll look at Inbutane. Inbutane's formula is C4H10. It's a pure hydrocarbon, has no oxygens. So the alpha must be 4. Alpha is 4. And the beta must be 10. Gamma is 0. So now it's simply a matter of filling the numbers in. So the coefficient of air is going to be alpha plus beta over 4 minus 0. That would be 13 halves. The coefficient of water, if we look down here, has got to be, the coefficient of water has got to be beta over 2. And beta was 10, so 10 over 2 would be 5. The coefficient of CO2 has got to be equal to alpha, and that's 4. If you run through this little bit of arithmetic, the coefficient of nitrogen is 24.57. So you can see it's just a matter of plugging in your values for alpha, beta, and gamma. Here I've shown an example using phenol. Phenol is C6H6O, or actually it's C6H5OH, but this is still the same formula. So alpha is going to be 6, that's the number of carbon atoms. Beta is going to be 6, that's the number of hydrogens. And this time oxygen is 1. This is just a matter now of filling in alpha, beta, and gamma in the general formula, and thereby developing the coefficients. Pause the video if you want and do it for yourself. My final example is 2,2,3-trimethylheptane, or C10H22, no oxygen. I chose this particular molecule because it's representative, at least, of the petrol or gasoline that runs a car. Again, alpha is 10, beta is 22. You fill these in order to develop the coefficients. The answers are given here. You can do the arithmetic yourself. Next, I want to introduce the air-fuel ratio, or AFR for short. It's just what it sounds like. It's the mass of the air divided by the mass of the fuel That's called the air-fuel ratio. Or sometimes it's called the fuel-air ratio, which is abbreviated FAR, and that's the mass of the fuel divided by the mass of the air. Do note that the masses are given in kilograms and not in moles. That's really the only complication to this whole idea. So mass is going to be molecular weight times the number of moles. You might wonder why we even bother to calculate an AFR. In this particular video, I've only introduced the stoichiometric balancing of hydrocarbon. However, if you know anything about running an engine, you know that you can put more air in or more oxygen in and be able to get more horsepower out of the engine. In doing that, that's going to modify the air-fuel ratio, and it's something that you might want to be able to calculate in the future in order to figure out how much more air you need to put in. So here I've shown the AFR calculation for each of the fuels that we looked at previously. Notice how this is done. We're going to have the mass of the air over the mass of the fuel. So for example, here we have the molecular weight of air. Now that's an average. We're going to use 4.78 moles of it, and this is the coefficient that was in front of the air. Down here for the fuel, we're going to have 1 mole of fuel because that's the way we developed the equation, and then we're going to have the molecular weight of the fuel. So you make that calculation and you come out with an AFR for butane of 15.42. The AFR phenol is going to be done the same way. This 7 was the coefficient in front of the air. There were 4.78 moles of air, and this is the average molecular weight of the air. This is the average molecular weight of the 1 mole of fuel. Finally, we've done the AFR for trimethylheptane, and that pretty much is the same calculation. So this concludes my presentation on balancing the combustion equation. I hope you've enjoyed the video and that you've learned something. Come back. Thank you.